The next topic is a groundbreaking idea that helps to reduce CO2 emissions. Did you know that a large amount of carbon dioxide is emitted during the manufacturing of concrete? Today's Takumi, or innovator, is tackling this issue from the perspective of the United Nations Sustainable Development Goals.
Cement is a key ingredient of concrete and is produced by heating limestone. When this happens, a large amount of CO2 is emitted. About 4.2 billion tons of cement are produced globally each year. This releases about 3.3 billion tons of carbon dioxide into the atmosphere. But concrete is a building material that is all around us and essential to our modern lives. Is there a way to reduce carbon dioxide emissions? Today's Takumi is taking on this challenge. We visited his company in Hokkaido Prefecture's Sapporo City. The Takumi is Aizawa Yoshihiro. He is the president of a concrete company founded in 1935 by his grandfather. Aizawa says that conventional concrete has an unavoidable drawback.
コンクリートって引っ張りにすごく弱いのね。力が加わるとこういう亀裂がパキッとこう入ったりするんですよ。このコンクリートの弱点をどういうふうにこう克服していくのかっていうのが我々のずっとこの業界全体のですね。課題だったんです。
Water is a key component of concrete. As time passes, moisture inside the concrete evaporates, causing the volume to shrink and cracks to appear. Aizawa has developed a product that overcomes this weakness.
コンクリートのこの亀裂、入ったクラックを自分でこう埋めてしまう。そういうメカニズムを我々作って産業化した。
Look closely at the surface, and you can see that the cracks are filled with a white substance. In this experiment, the product was applied to these cracks, and 2 weeks later, the damage had healed naturally. Incredibly, it repaired itself. How does it work?
自分で直すコンクリートにこのパウダー状のですね粉が配合されてます。でこの中に実はコンクリートの中でもかなり生きることができるバクテリアが実はあるんです。
If we look at it with an electron microscope, we can see the bacteria. It is the action of this microorganism from the Caspian Sea that repairs the damage. Let's have a look at the theory. When manufacturing concrete, a powder made of bacteria and a polylactic acid they feed on is added. pH plays an important role. Concrete is usually strongly alkaline, with a pH of 12 to 13. In this state, the bacteria are dormant. The polylactic acid is broken down by moisture and alkaline components and changes into calcium lactate. The concrete deteriorates over time and cracks occur. When water and oxygen get inside, the pH drops to 8 to 10. This causes the bacteria to become active. The bacteria take in calcium lactate and oxygen as food and excrete calcium carbonate. This calcium carbonate fills the cracks with the same components as concrete. The lifespan of standard concrete is about 50 years, but this is expected to help concrete last over 100 years. Extending the service life of concrete reduces production and therefore reduces CO2 emissions.
この自己中コンクリートを最初に上市した時に一番最初に掲げたのがデカーボナイゼーションファーストです。
Aizawa originally worked as a newspaper correspondent in the US. At the age of 43, he took over the concrete company from his father. However, he had mixed feelings about the industry.
やっぱり小さい頃からね、コンクリートってどちらかというとですよ、イメージはね、非常にこう無機質で冷たくて反環境でみたいなね、ネガティブなイメージが非常に強いかったわけですよ。
He wanted to develop new products and change the image of concrete. While looking for ideas and reading research papers from Japan and abroad, he came across research on a bacteria that causes concrete to self-heal from the Delft University of Technology in the Netherlands. Aizawa immediately visited the Netherlands. He set up a joint research project and started developing a product. However, he came up against a big obstacle. This is a sample of bacteria and polylactic acid made by the university research team. The polylactic acid is manufactured into a rod shape, like spaghetti. Bacteria are injected inside at 1 millimeter intervals. The rod is then cut into pieces. However, this method was too costly and could not be mass-produced.
アイデアはいいんだけど、実際の産業製品っていうのはやっぱりその量産技術っていうのが初めて組み合わさってね、テクノロジーっていうのはやっぱりこう世の中に広がっていくもんですから。
Aizawa needed to find a way to keep costs down while making large quantities. He came up with the idea of simply mixing the bacteria and the polylactic acid. However, the difference in particle size of the two ingredients was a problem. Bacteria grow and form aggregates of 100 micrometers, while the polylactic acid is about 10 times bigger. Self-healing doesn't usually occur unless materials with different particle sizes are mixed uniformly. As he continued his research, he found a device used by a German company for mixing cosmetics and pharmaceuticals. The secret to mixing the bacteria and polylactic acid is the mixer's internal structure. There are two sets of blades for mixing. After the device is sealed and decompressed, the outer blades rotate 34 times per minute, and the inner blades rotate 2,000 times per minute. As a result, the polylactic acid binds around the bacteria to protect it. This enabled mass production and ensured the bacteria's survival.
200万都市の札幌がね、1年間で使うコンクリートの全てを自己中化することができる。それだけの能力を持ってるんですから。
This product is now being used in various structures, such as the water quality management facilities of a waterworks bureau and Japan's largest fish farming facility.
脱炭素に資する材料だとかテクノロジーっていうのは基本的にオープンで誰でも使えるようにしようとしてます。我々の同業ですよね。本来であれば競合するね他社さんですけども、そういった会社さんにどんどんこの我々のこの材料を扱ってもらうようなその集団的な動きを今し始めていて。